Here we are once again at the physics video lecture. Welcome. This is physics 4B video lecture 20. We're talking about magnetism and in particular the motion of charged particles in a magnetic field. And then we'll move on to forces on current carrying wires and stuff. But let's stick with the charged particles for a moment. Charged particles in a magnetic field, in a B field. And what we had was the force law, sometimes referred to as the Lorentz force. It's the charge times the velocity across the B field. Okay, so that's a pretty complicated force law, and in particular you have to know the properties of this vector product V cross B. And then you see that if the charge is at rest, there's no force, which is kind of interesting. And because if you reverse the direction of the charge, you're going to reverse the sign of the force. There's also the direction of the velocity. You've got a sign, potentially positive or negative in the charge. So there's a lot going on here. But what we found was with a uniform magnetic field, we can get these circular orbits, a circular motion. Okay, so there's the force. And as a note, if you're doing Newton's law for the forces on a charged particle, we had mass times acceleration equals, that would be the force due to the electric field, and now we have the force due to the magnetic field. And in both of these, if you divide both sides by m, you're always just having that ratio q over m. So just using Newton's law in this form, you cannot determine the charge or the mass individually, but only their ratio. Okay. So only q over m can be determined using this equation star. On the other hand, that's an important thing to determine, and if you can get the charge or the mass by some other means, then you can get the charge and the mass. So only q over m can be determined using this equation here, the dynamics. We're going to go back to and look at the circular motion a bit, and I won't demonstrate to you, but I'm going to show you a device that we'll try to use later. So we saw this last time, so I'll go to uniform circular motion. Suppose we have a charge moving in uniform circular motion. So it's right here. Okay. There's the mass. That's the velocity vector. Of course, it's perpendicular to the radius vector. And QV cross B. So if we had a V and we cross it into a B field, say we had a positive charge, we cross that into a B field that is into the board. That's what will give us the force directed towards the center, okay? We get, so a uniform field in or out of the board here gives us a centripetal force due to centripetal force and m comma q positive often easiest just to work with a positive charge, and then if it turns out to be a negative charge, you reverse the sign, okay? So if we have a positive charge here, then we would have B into the board everywhere, okay? Into the board. Good, so uniform circular motion is due to centripetal force. We're discounting the E right now, there's no electric field, so we just have M A centripetal is equal to Q B B. That's the magnitude of that expression right there. So M V squared over radius is equal to Q V B. So we can strike one of the V's there. So I'm going to write V over R is equal to Q divided by M times B for the moment, okay? And let's just call this 1 here. So you have a relation between the speed and the radius, and this is the actual radius of an orbit of that particle. And if you have a stream of particles, then you'll actually see, and you have it in a vacuum tube with a little gas in it, the right kind, you'll actually see a circle. You'll see an illuminated circle. Now, that's the first expression here. We got that right? Yeah. Now, what about V? How do you get the speed V? So, to bring particle up to a speed V, we have to send it through an electric field or through a potential difference. What we do is this. We have Q delta V turned into kinetic energy. Remember the work kinetic energy, so this is Q delta V turns into 1/2 mv squared. So I'm calling delta V the voltage, Q is the charge, V here lowercase, that's the speed squared. Okay, okay, so let's continue with this. Yeah, so let's go ahead and solve for V here. What we end up with is V is equal to, we've got a 2 delta V multiplying over, we have a Q over M, and we need the square root of the whole thing. Okay. So again, I'll take square root of both for reasons here. Again, we see the dynamics on this thing, and this was just the work kinetic energy theorem, work kinetic energy theorem. Again, these dynamics just don't allow us to get Q or M individually, but Q over M. We can take that into this expression over here. I could just leave it here, but let's go ahead and go ahead and solve it. So now we have a 1 over R, this V is root 2 voltage difference, so voltage, and then root Q over M, and on the right side we have Q over M itself times B. What I'm going to do is just solve for Q over M, okay? So Q over M, well, I can strike this, and now I have a root right there. So root Q over M is equal to 2 delta V root over B times R, and we'll just go ahead and get an expression. So this is what we're looking for, right? This is what our experiment's going to give us. 2 delta V B squared R squared. Now let's think of this as an experimental situation where we can adjust the voltage with which we accelerate those particles. We can adjust the magnetic field, and in making various and assorted adjustments like that, we can also adjust the radius. So we have a device that we like to do a lab with, and I like to demonstrate in class, in which we do adjust the voltages and the magnetic fields in a controlled way, measure the changing radii, and take some data, and then actually get the charge of the electron divided by the mass of the electron. So I'm just going to show you that device, because I actually need some tech support to make it work here, because it requires a dark room. But this is the device, and I'll just point out a couple of things. The vacuum tube right here is where all the action takes place, and I'll draw on the board what happens then later. You've got a vacuum tube here in which the electrons do their circular motion. The magnetic field is produced by the current in these wires. That's the content of the next chapter. Very interesting that you produce the necessary magnetic field in wires, and it's sufficiently uniform at the center of that vacuum tube there. So possibly I'll get some tech support in a darkened room and we can make this work, but as it is right now, I'm not able to do that. But in the next chapter, we're going to come back to this anyway. Good. So let's go back to the board. Yeah, I'll just draw a little picture underneath here. So yeah, what we have is that vacuum tube there, and that has all of the stuff inside. So what I can't show you without a very darkened room and some different setup is that we accelerate our electrons. In fact, if I had a green pen, that would be the color of the electron beam. So we accelerate the electrons in this direction through a little voltage here. And we end up with a B field that's coming out of the board due to those coils that I just showed you that we're going to do the calculation for next chapter. And here we'll make the circle red, and we get a circular orbit inside of this thing. And just by dialing up or down the voltage, we can make the circle larger or smaller. And dialing the current up and down, we can get the magnetic field. So we can actually control this radius of these circles of electrons in orbit. We can control the radius by changing the magnetic field and changing this voltage difference. That's one of the great labs that we should all do. And so I'm going to see if I can get that as a demonstration. And we take radius measurements. In fact, this device has a little built-in ruler. We used to have to stare at it really carefully with holding up a ruler behind it. And so yeah, we're able to make a sufficient number of measurements to graph the data, and like voltage versus radius squared, that type of thing. And the slope of our straight line that we get out of those data is then E over M. So very important and interesting demonstration and lab. Okay, so that's what we have for now. And we did a few problems on that, and eventually we'll do a quiz of this type. And what you really have to remember is just the basics. So you don't memorize any of these formulas, okay? Because that may not be the way we need it. What we do is we just set it up. You know, Newton's law, mass times acceleration equals force, and then we just work our way through to some useful expression. So we've done several of these, and that's why I'm trying to drive the point home. and we'll return to that. Okay, let's see what's next. Yeah, put some words there about taking data and so forth. We'll send this up. Okay, so moving charges are not only in a vacuum, they're also in a wire. So we're now going to talk about forces on conductors that are carrying a current. But the generalization is actually pretty quick. So forces on current carrying conductors. And what we do is we just begin with this force that we had, QB cross B, and now we just generalize, right? We have charge times length per time, and that's just going to turn into F equals current times a length element across the B field. Okay? One follows directly from the other. And right, the dimensions are trivially the same, right? Charge, length over time, and then we have charge over time times length. Okay, so this works. Now for a short length of wire, actually make sure I don't have anything in between here. Yeah. So this is for a straight length of wire. Okay. So I'm talking about current and length, and because it's straight, I can associate the direction of this with L, and that's why I could put a vector over the L. Okay. But for an arbitrary shape, we have to use a differential. Talking dF equals I, and we'll have a directed infinitesimal element cross B, and then we can integrate this up for the total force on some length of wire that, you know, looks like this. Okay. Starts from here, ends up here. Those are 2 points in space, and it's carrying a current. It's very common to bend the section of wire into different shapes. So yeah, for an arbitrary shape, we have this, and then the total force would be the integral. And we can pull the current out because we are still discussing a constant current. ds cross B. Good. So we want to do a couple of examples with this. And I've assigned these as homework problems, but I'm going to do them anyway. So, you know, you look at it on the homework, come back to this and have a look. So the first example is if B is constant, then we can pull it out of the integral. If B equals constant, we'll go up to B. And of course, it's natural. Most of the things we can calculate, or it helps a lot if B is constant. Okay. But we can produce constant B fields. We get one for this experiment. I showed you last time between the poles of a magnet we can get a nice constant B field. So good, if B is constant, what do we have here? It's still a vector, but what we can do is say we've got I integral ds, right? And we can do the integration and cross the result of that with that B field. And I'll just say from A to B. Okay. But the result, and let's use that picture over here again. This is interesting. So the result, A to B, remember this is just the sum of infinitesimals. So we could say we have a bunch of little arrows like this. But we also know adding arrows means we just have a resultant. So this thing here, regardless of the curve, it's just equal to the difference of the endpoint vectors. Okay. So in other words, it's equal to this red one here, which we could just call B minus A. And we could have done a couple of loops of the loop before we get to B. It would be the same thing. So yeah, that's it. That's an interesting theorem, you could say. For if the B field is constant, this integral, which seems like it would be very, very complicated, just turns into I times this vector B minus A crossed into the B field. Good, so that's a homework problem, but you can come back and use this to construct your proof. And another example, furthermore, actually this is so important, I don't know why I'm just going to squeeze it into the bottom corner of the board. However, what if we have a closed loop? Right? A closed loop, this was a point in space, an integration sum of all these little infinitesimals along a closed loop is equal to 0. So that means the net force on a closed loop in this B field, uniform B field, is equal to 0. So furthermore, if the loop, if we integrate, or just furthermore, all right, for a closed loop, this integral ds is equal to 0. Okay. And as such, the net force on that closed loop is equal to 0 as well. So that's a really important point that we're going to make use of. But there's also an interesting problem where we can demonstrate that rather nicely. So let's do that over here. So yeah, this you will find as homework on our list. And also this one. So let's calculate this example. And that is that we're going to have a semicircular loop. Okay. So we've got a current going this way in this semicircle, radius capital R. And I'll go with what my notes are. Yeah. So we're going to have, let the B field be uniform, right, in the plane of the board and vertical. And our current here is just going around the loop as I'm showing here, counterclockwise. So what about the force due to the straight wire? So forces, straight wire, well, that one's pretty easy, right? I times 2R, so F is equal to I L B, so I times 2R times B. And what's the direction? So turn this vector, cross it into B, so it's coming out of the board. So the direction, wait a minute, out of the board is like that, okay? ILB, I, 2R is the length, B, out of the board. That's the straight segment. What about the semicircle? For the semicircle, first of all, right when we start here and when we end up there, that little increment is parallel to the B field and of course contributes nothing. So it's going to be this part that contributes, and so if we cross this little ds into B, cross this into B, it's into the board. So the contribution of this semicircle is going to be into the board, and the force here will be this integral I, and I'll first write down what we have here, ds cross B. B is constant, so I need a little more room for this. So the direction we already have. So we know that the direction is into the board. And we just have to construct the magnitude of that integral. So what we have is, and I should label these one way or the other. So yeah, this is I and this one would be double I. So yeah, the semicircle, yeah, what do we have? I integral. Now the ds is just going to be an r d theta, okay? And crossing that into B, and the integration is going to go from 0 to pi. And if you remember the rule for the cross product, it's going to be B, so we got R, B sine theta. So B times the sine of theta. Like I said, I've got the direction there. So let's go ahead and do that. We have I, R, B. Remember, this is by the definition of the cross product. Good, so IRB, integral sine theta d theta, 0 to pi, IRB cosine theta, or negative cosine theta from 0 to pi, and that is going to give us a 2. So we end up with 2, positive 2 by the way, make sure you write that out. 2 IRB, and that's what we had here, 2 IRB, but this time it's out of the board, which means that they add up to 0. So the interesting and important thing is they add up to 0, so it is a closed loop, and the net magnetic force is 0, but there is a torque involved. If we imagine an axle through the middle of this anywhere, we could see that there would be a torque, because we would have a couple. We'd have force coming out and force in, and a twisting. So that is the next. So we see F net equals 0. Those are two vector contributions in different directions. They cancel each other. But there is a torque. of motors and transformers and other interesting things like that. Then you have torque on a current loop, even though the net force is 0. Okay, good. Let me consult the clock here. So for the torque on the current loop, we'll do a little construction as well. Torque. And perhaps we'll do a drawing first, yeah. There is a torque. So the next, I'll go ahead and send this up. The next discussion is torques on current loops. So we've got a conductor carrying a current. It's bent into a loop, and we want to calculate the torque. Okay, good. Let me put this in here before we get lost. All right. Torque on a current loop. So we'll make this pretty symmetric. Let's have the B field like this and the board pointing to the right. And now we have a current loop. I'll give it different dimensions. And we can imagine, we don't have to, but we can imagine an axle in the middle here. So what I have here is A and B, lowercase b. So the area is going to be A times B. And we have a current, we're going counterclockwise. Okay, so there's our current. So what are the contributions here? These two are parallel to the field and they're contributing nothing, there's no force involved. If we take this one here, I cross B is going to be into the board. Therefore, I cross B on this one is going to be out of the board, and we've got that torque, right? This is this thing here, and there's a twisting force. And for symmetry purposes, I just put this axle right in the middle. But yeah, we have a torque, and tau is going to be F1 times A over 2, which is the lever arm. We have F2 times A over 2. And they're both going to be ILD, which is I times B times B times A over 2, and the whole thing doubled. So here's the thing, these cancel, we have I times A times B. This, of course, is the current, this is the magnetic field, and this is the surface area. And this generalizes really nicely because what you end up with is a generalized expression where you just have a surface area and a current and B. And if you choose a generalized direction, this product is going to turn into a cross product. So I'm going to write it down first and then we'll analyze it. So generalizing this, now let A vector be the surface normal of that area times the area. Okay, so we've got, in this case, the surface normal is coming right out of the board at us. Okay, surface normal, and then we're going to continue to define U as the magnetic moment. We're using mu here. Yes, we are. I times A and then we're going to end up with F is equal to mu cross B. So this magnetic moment is containing the current and the directed surface area. Very useful for little loops. Current, the directed surface area, crossed into the B field, giving us, actually not the force, the torque. Torque. Yeah. Yes, the torque. Okay. Which is also a vector. So magnetic moment. Now this is just for one turn, but if you ever look at any devices and coils, you see they have many turns, and having done this once, it just suffices to multiply this expression, the right side, by the number of turns, and we just get greater and greater torque proportionate to the number of turns. So I'll put that down as our finished expression here. Yeah. For a coil with n turns, torque is just going to be n times mu cross B. Make sure that's what I'm running with. Yes, that's what we're running with. N mu cross B. But yeah, this is just a generalization. So here we had an A times B, and it was a rectangle. If we had a circle, basically the integral that we did with the semicircle, that thing completed would give us the same expression with the area. Okay. So yeah, we have magnetic moment, but this goes back to the directed area, which is perpendicular, or which vector stands perpendicular to that area, right? Actually, the standard area element, directed area element. Okay, I think we'll leave it at that. This is going to be the basis of electric motors and other things. I want to put up, yes, a homework assignment. Almost forgot. So this is homework number 20. We will have, I think there's one problem or two with those as well. We have chapter 26. So two problems, 25 and 26, go back to our circular orbits, charges in orbiting in a circle. Then we have 47 and 48. Remind myself what those are. Yeah, those are coils, no problem there. And then 70 and 71 were forces on a wire and forces also circular orbits, 70 and 71. Yeah, the circular orbits are important. Good, that's homework 20. See you guys next time.